right? So 265, this question, this is a really tedious one, right? Uh, so wait, not 265. What was it? It was, yeah, 265 actually. Right, so small body A is fixed to the inside of a thin rigid hoop of radius r, mass equal to that of body. The hoop rolls without slipping over a horizontal plane. The moments when body gets into lower position, the center of hoop moves with velocity v naught. At what value of v naught will the hoop move without bouncing? Right. This is the figure for this thing. Yeah, try it out. It's easy if you know the details, but if you don't, you might get stuck. Like, how do I figure out when is this going to bounce? What's the condition for that? So we can definitely figure out when it's not going to bounce. It will not bounce if the normal force throughout, I mean, if it's in contact with the floor throughout, right? Which means normal is bigger than or equal to zero. And whenever normal is less than zero, so the expected normal, that just means that it's actually not in contact anymore, and it's bouncing, right? Because what normal less than zero actually means is that you need a downward force to keep it in contact. So it has a natural tendency to bounce upwards, right? And then you actually have to figure out a normal as a function of theta. So theta is the angle that this makes with the vertical or whatever you want to call it, right? So you have to do that. And once you're done with that, you have to figure out when is this normal force the minimum. And at that minimum, it should not be equal to zero. Okay, it should not be less than zero, right? That's what you have to guarantee. And once that's done, you can definitely say that it will actually be, rolling without bouncing. That makes sense. The whole problem with this thing is that it's really hard to first of all figure out the normal in terms of theta, because for that you have to do some energy stuff to figure out omega square. Once you do that, you have to figure out alpha by differentiating, and then once you do that, you will get the normal force by applying the laws of motion on this complete system. So yeah, multiple steps in the process, but once you do that, you will get an expression. Now the real problem starts. Minimizing that thing is just so hard. It has three terms, and two of those terms have something. Okay, b minus cosine theta, something like that in the denominator. So b is just some kind of constant, right? I'm calling that. Yeah, and then you actually have to do that, right? Minimize that and get the thing done, and then you have a, another problem with that because your v naught is variable, right? We don't know what your v naught right now is. So yeah, you can't even use the fact it's like motor increasing or something like that. You can't. It just gets so complicated, right? Yeah. But after all of that is done, you will get this information for very big V naught value. So when I say very big, I mean bigger than a certain critical value, right? So there will be a critical value where this, yeah, I mean, actually it will have a minimum value at some kind of theta value, right? It will still have a minimum, of course. What I'm saying, it will have a minimum for some cosine theta value, right? So if you represent normal as a function of cosine theta, so just substitute c equal to cosine theta, then yeah, you will actually have a minimum value for some cosine theta value, right? So you got something like that in negative 1 to 1, right? In that interval, if you get the minimum value, right? So if it's more than that critical value, so if it's more than that p naught, then you will never get. What's this thing? Is this an insect on my desk? Wait a second. Oh yeah, it is an insect on my desk. Whoa. Right, sorry. Just an insect on my desk. Nothing else. I think it came in because it's raining outside. So whatever. What was I saying? Yeah, if your V naught is more than that value, you can just be sure that your n minimum that will happen when your point so A is completely at the top, right? And that is when your cosine theta equal to negative 1, which is the lowest value for cosine theta. So the thing is dn upon dc, so c is just cosine theta, that will be positive when your V naught is something more than a critical value. And yeah, in the range negative 1 to 1, of course. And when that happens, it's just going to be at the top that you have the minimum value, right? I mean, think about it. If it was minimum at some point, some other point, right? Then yeah, shouldn't that be zero at the point or something like that, right? You could ask something like that to yourself, and then yeah, it just feels more natural to think that on the top you will have the minimum n value. Okay, even though that might not be reality sometimes, but for this kind of condition where it's we want it to bounce, right, or want critical condition when it will not bounce, you can assume that. So even if it was not like a ring, even if it was a disk or it had some other mass, you can still do that. Okay, you can still assume that, and then once that assumption is there, so yeah, just figure out uh, what the value of normal will be at this point, right? And yeah, that's gonna be the thing. Okay, so let's do the thing, right? What do we have? First of all, we get an expression for normal, right? So you got normal force from here. You got mg and mg force. So capital M is just the mass of this guy. We know it's gonna be equal, but whatever. For now, just do this thing. Right. These are our, you know, actual forces on this system. Now, the y acceleration of this hoop is 0 because it's like in contact with floor, and the y acceleration of A, that is just the y acceleration with respect to the center of hoop plus the y acceleration of center of hoop, which is actually 0. So it's just a, yeah, it's just y acceleration with respect to center of hoop, which is just the centripetal acceleration, right? So okay, the y component of that, of course. And yeah, there is the tangential acceleration, but then think about it, we don't care about it because we just want it to be at this point, right? Okay, you know what? Whatever, I'm gonna do it for you. I'm just gonna do it for some general theta, although I don't want it to be like that, but whatever. So this is our theta, some general theta. We don't know. You got this over here, right? So your acceleration for this guys, like it's r alpha in that direction, and it's okay, it's like this actually. So it's omega square r in this direction. So the y components, this is like theta. This is going to be theta as well. So omega square r cosine theta. Okay, so our acceleration in y direction is omega square r cosine theta. All right, and then you got this. This is going to be yeah, sine theta. We know that. So like just alpha r sine theta. But the thing is, this is times our small m. So that is the net force. And this will just be equal to the normal force minus mg minus mg. So yeah, what we want is that at the topmost point, which is when cosine theta is equal to -1 and sine theta equal to 0. So we're just going to have what? Negative m omega square r, right? Because yeah, I mean, you just completely downward, right? That's the acceleration. The curvature is downward. That makes sense. Okay. So negative m omega square r, that is equal to n minus mg minus mg. That is our condition. So actually not this condition. We would want our normal force to be 0 at that point. So this is our real condition. So in this particular case, m and m are the same. So what you can do is just say omega square r is equal to 2g. Okay. Now, the thing is, we want to figure out what omega square is. So first of all, energy conservation, that's the thing to do. So the potential energy, right? If you think of this as the bits like the potential energy at this condition to be our baseline, right? So whatever energy you have would that be 0. Then the potential energy of the system is given by, so what is the height of this thing? Just like 1 minus cosine theta. So yeah, mg times 1 minus cosine theta. And what's the kinetic energy? So this is a slightly more complicated. So yeah, you can use the fact that this point is, so the contact point is actually at 0 speed, and then use the fact that all of this is like this complete system is just a single rigid body, and then you can easily write it half I omega square. That is your kinetic energy. But the thing is, inertia is a variable quantity, depends on theta. So just to make your work a bit easier when you will be deriving it by yourself, and I know you will be, because if you're like me, you can't just be satisfied by my explanation. So I'm going to do this for general theta, but then we actually just need to do this for, two conditions, whatever. So figure out the kinetic energy, right? Okay. So this is our thing. Yeah. We just want the, first of all, inertia about this point. So for this complete hoop, it's just 2mr squared, right? And yeah, I mean, you could generalize this, right? What's the big deal? You are going to do it by yourself. Okay, and this, right? So this is also part of the inertia. So m times this thing squared, but what is this thing? So you can think of it like using vectors or whatever. So this is, Yeah, and this is like theta. So this is this vector minus that vector, and you want the square of the resultant. So it's like this is this squared plus that squared minus 2 times of this times that, and then cosine theta. That makes sense. All in all, it's just what 2 times of 1 minus cosine theta times times capital R, right? Yeah. So there's this length squared. Okay, like R squared times 1 minus cosine 2R squared times 1 minus cosine theta. That makes sense. So 2r squared plus 1 minus cosine theta. And then you got the mass small m. So this is the thing, right? So all in all, you just have 4mr squared minus, right? I mean, that's correct, right? This thing squared is that r squared times 1 plus 1 minus 2. Yeah, of course, it is the thing. So just 4mr squared minus 2mr squared. And you know what? Just take 2mr squared common. Who cares? So it's like 2mr squared, and then you got this thing. 2 minus cosine theta, right? So this is our, sorry, this is not the kinetic energy, it's just the inertia. So it's the inertia about the contact point. So the actual kinetic energy will be, just wait a second, kinetic energy that will just be half I omega squared. So yeah, like mr squared times 2 minus cosine theta times omega squared. So remember, actually this is a, like omega is a function of theta, so this is changing, this complete thing is changing as a function of theta, right? Okay. So energy conservation, kinetic potential energy, what is that going to be? Okay, actually, you know what? Right, okay, let's just take that m out because we don't. So u plus k upon m, that is just going to be g times of 1 minus cosine theta plus omega square r square times 2 minus cosine theta. So initially, this thing was just equal to what? Well, theta was 0. This thing would just have been 0. And then what about this guy? It's like just 1. So it's just equal to omega square r, right? Oh, omega naught square r, I think. Which is basically like, it's like r squared. Yeah, it's r squared. And isn't that just, v squared, right? I think I might have messed it up somewhere because half I omega square. Well, yeah, I mean, you just got like v squared, it's like half m squared. That makes sense, sure. And then oh, there's supposed to be an R over here. Why is there no R? It should be there. Yeah, kind of a silly mistake. Okay. So this is equal to what? Finally, just got like omega naught squared R squared. And then, you know what? Actually, I really just want to write it as B naught squared, but then whatever. I mean, omega naught is also a good thing to use. So R squared. And then you got this thing. Just one. That's 0. So there we go. That's gonna give us our omega. So first of all, R cancels, right? One of these R's just cancel. Then you got this thing, omega squared r times 2 minus cosine theta is, and okay, like, okay, fine, whatever. This is like omega naught squared r, and you got minus g plus g cosine theta. Now you can see what was I saying, right? This is, yeah, first of all, you have to figure out an expression for omega squared, and you will have to use that in this normal thing, right? Where they go. Yeah, right. So to get the value of normal at every single theta, and then it just becomes so much more complicated. So don't do it. Right. Now, we only want our omega square for the topmost point. We don't care about all the other points. So what we'll do, just put theta is equal to pi, then do the thing. So it's like what? Omega squared r times, what is this? It's like 2, 3. It's just equal to, okay, that's going to be what, -1. So omega naught squared r minus 2g. So this is a one equation that you have. What was the other equation? This thing. So it was just yeah, well, capital mg plus small mg is equal to small m omega squared. Okay, that's actually not important. This is the thing. Omega squared r equal to 2g. So this is just equal to 2g, right? That's what conditions. Like what you have just got 6g is equal to omega naught squared r and then minus 2g. So what do you have? You just have 8g is equal to omega naught squared r. So this thing can just be written as v naught squared upon r. Because of course, like you can see that, right? V naught is just omega times omega naught times r, right? So v naught is just square root of 8gr, right? Yeah, that is the thing. Right. I didn't explain this in detail because I don't want to get into a lot of maths, which took me hours to do, right? Go through that suffering yourself. I don't want to do that. But that's the way this is done. Okay. I mean, when you're on a test, you will of course do it this way, not the proper way, because then you're wasting time on something that doesn't actually matter for our answer again, right? There we go. Next question. Yeah, I thought I would make a note for this, but no, no, no. It's just a lot of math. There's nothing intuitive about this result, like some other way you could. No, I don't have anything like that. It's just a lot of calculation. So it's not worth to make a note. I mean, even something as simple as just showing that n minimum will be at this point for big V knots. Yeah, it's so hard. Okay, so that was 25th, right? Okay, 265th. Okay, one second, what was the question? What did they ask? Right, so the value of V naught such that this happens, right? Okay, next. 271. A uniform cube with edge A rests on a horizontal plane whose friction coefficient equals to k. The cube is set in motion with an initial velocity travels some distance over the plane and comes to a standstill. Explain the disappearance of the angle. I think I've seen this once. I don't know. Disappearance of the angular momentum of the cube related to the axis lying in the plane at right angle to the cube's motion direction. Okay, plane in the floor basically. Right, so I think I get what this guy's saying. So you got this cube, which is gonna draw it in 3D, you know. This is the axis they're talking about. So, okay, if you got like this is our point, it's our origin basically, right? Right, and then this is our floor. Can't draw it correctly this time, but whatever. And then you have friction acting on this thing. So you might, okay, the friction doesn't actually put any torque on this thing, right? Because, yeah, so there's no torque because of the friction, and right? There's no torque because of friction, so there must be no change in the angular momentum of this system, right? But we know that this guy goes from some velocity to some not velocity, right? It stops after a while, and then like this guy's velocity is like, yeah, its total angular momentum about this point is actually not zero everywhere. When it has velocity, like this will be this arm length cross that you get the thing. So angular disappeared. Why did that happen? Well, there's a problem in considering this as our system, because what we are doing is we're taking, you know, this floor, right? We are taking the force exerted by the floor onto this block into consideration, but by Newton's laws of motion, we know there's an equal opposite force. Why are we not taking that into consideration? Because throughout our derivations, we always took that force, right? Yeah, we always took that force into consideration. Why are we not doing it right now? Because, yeah. So what about that, huh? Is that not like supposed to be, they're supposed to be the earth, they're supposed to be earth. So this earth actually gets the angular momentum because of this force, right? So no, angular momentum is not lost, it's just that you don't know what the system actually is. And that's good and all, but what about the t equal to I alpha for just this system? What happened to that thing? So well, you might say that okay, the velocity of, you know, this guy is actually like, okay, it's going like in this direction and whatever, right? So now it stops, it loses some angular momentum, but you are taking the wrong coordinate system. You are taking the coordinate system fixed to the earth, right? And doing everything according to that. So because earth is not an inertial frame anymore, it's actually, yeah, it's also accelerating, right? So you have to apply pseudo forces and whatnot, and that would somehow make this work, right? Equal to I alpha would still work. The easiest explanation is, of course, take the Earth into our system as well, and then it explains what's happening. But if you want why t equal to r alpha is not working, right? It should work. Thing is, you got this Earth, you got your block. I know it's very exaggerated. Earth is not so small, and then you got this point. Okay, so initially it was having like a friction force, right? Yeah, and that friction force was not actually doing anything. Now, as this block moves on the Earth, what's happening is that Earth is experiencing an opposite, right, thing. So, okay, how do I explain this? Friction is in this direction for this guy and in that direction for that complete Earth, right? So accordingly, we'll have like some velocity of this thing, right? And then you got some. It's just hard to explain, isn't it? Yeah, it kind of is hard to explain. Okay, instead of like having this as okay, I mean, there are just too many factors that I can't explain right now. First is like Earth is moving with some velocity because of this thing, and then it's rotating and whatnot. So, yeah, how do I do this thing? What if instead of Earth you had something else? Okay, no, no, it's just getting too complicated. But yeah, most likely that's where the t equal to I alpha is coming from because your coordinate frame is also moving. Because if you are fixed on the Earth surface itself is moving. So you have to take that into account as well. If you're not fixed, then you have to take into account, you know, the fact that the velocity at the block has is actually different than what you think it is, right? Do I make that understandable? Because right now we're thinking the block is like going with velocity v, and then it stops, right? But in the other reference frame where we are not fixed to Earth, it might not stop in the end. It will still move with some kind of velocity, and then there's a lot of factors that you have to take into account. So I won't explain everything, but give the idea about what to think. Okay, so that explains it. Done. 272. Anything? Any other sub question? Find the distance between the resultant of gravitational forces and the reaction forces exerted by the supporting plane. What? Resultant of the gravitational forces and the reaction forces. Wait, wait, I didn't understand what's going on. Oh, okay, okay. Like, yeah, I didn't take that into account as well. Oh, right. So, I should have yeah, okay, that explains everything. So there's friction, of course, but somehow I forgot about mentioning the normal force, which is also important. So usually we like don't think about it all that much because, right? But in this case, we have to think about it. So yeah, you got this block, it's moving like this thing. You got the friction force, which is not providing any kind of torque. So yeah, you might actually apply it equal to I alpha in this. Right. So what if you don't have the actual thing? You don't have Earth, right? You don't have the Earth to explain what's happening, why is like angular momentum disappearing and everything. Okay. And instead, it's a hypothetical scenario where this float does not actually move, and then you have an external friction force on this thing. So right, this is still our system, this block. That's the thing, that's our system, and this is our origin, right? You have this external friction force on this. Then now, can you explain why is the angular momentum disappearing? Because now you don't have the Earth to say that, okay, the angular momentum that we lost is actually going into the Earth. You can't say that anymore because you already said that this is not moving, right? And F is an external force, okay? So now what's going on? Why is T equal to I alpha not working? The thing is there's a normal force. This is normal force, and if you look at it, the torque because of this normal force is not zero. So, okay, that actually is a much better explanation, I think. Right, that explains is much better. There we go. Okay, and then you want to find the distance between the resultants of the gravitational force and the reaction force exerted by the supporting plane. Reaction force, but it's just the normal force plus this thing. Okay, okay, that's kind of weird. So yeah, there's gravity, which is also in this case an external force. Previously it was not, but yeah, you got gravity. Usually you just say like there's no force in the y direction, but yeah, I almost forget about this normal force, right? So normal force might be not in the line of action of gravity, and that because of that, you got this torque canceling out with the. Okay, that makes sense, right? With angular momentum. Okay, so now they want us to find the distance between the resultants of the gravitational forces and the reaction forces exerted by the supporting plane. What is meant by gravity? Okay, just mg force and the reaction forces. So you got this as well as the friction. So that's weird. Uh, right. I mean, the friction could act at any point. It will still produce the same torque about this point. We don't care about that. Okay, about the center of mass. Yeah, about the center of mass, our angular momentum is zero throughout, right? So that would, I think, give you the point of application of friction force in that case, right? But normal force is actually easy to figure out. Okay, so you got normal force in this direction. There's some like thing happening over there. There's no force. Okay, you know what? Yeah, I mean, that's not the best way to do it. The friction force is just somewhere where, okay, yeah, like you got this. You have to go to the center of mass's frame. So you got this thing. The pseudo force will be there, but then because it's the center of mass, no torque because of that thing, right? So you got friction force in this direction, which we can figure out. Yeah, it's just like mu times mg. Okay, mu times normal. Normal is just mg because no y acceleration. Then you got normal force, which is somewhere. You got the mg force, which is not producing any torque. Okay, the torque because of this. So the normal force might be over here. It's just wrong. It's like somewhere over here. This distance is x. So what we have n times of x, which is like mg times of x, of course, because it's just mg. That is equal to mu mg times this distance, which is like a upon 2. So x is just equal to mu a upon 2. That's the thing. So okay, in this case, it's like k upon. I'm gonna use mu. So k a upon mu a upon 2 is our x. I think this was very like elementary, isn't it? Yeah, I just complicated so much. Okay, so that's done, and you want to find the distance between the resultants. So the complete resultant, right? So this is the normal force, and you got the friction force over here. So you can just combine these, and then you got this as a thing. So the actual point of application of the total force is like x, and then you got this a upon 2. So square root of x squared plus a upon 2 squared, which is just a upon 2, and then you got square root of mu squared plus 1. So this is the distance. Okay, this is the point of application, and you also want the gravitational force. This is a point of application, which is at the center of mass. So this really is the distance that we want. That's it. Next question. And this is like q. This is mu. It's different. Okay. So there we go. That should do it. Oh, that's like a. Sorry, not u. So a upon 2 square root of mu squared plus 1. Next question. 272. 72 is a smooth uniform rod AB of mass m length L rotates freely with angular velocity omega naught in the horizontal plane about a stationary vertical axis passing through its end A. Okay, rod, this is end A, this a small sleeve of, I think I've seen this. Yeah, we have seen this. Okay, start sliding along the rod from point A. Find the velocity v dash of the sleeve related to the rod. So related to the rotating reference frame, of course. At the moment it reaches its other end B. Hmm. A small sleeve of. So you got R alpha and everything like that, but then this guy is going with velocity omega naught. It doesn't change. So okay, that part is not there. But wait, there was the other part as well, right? Of course, we have to take that into account as well. Oh god, okay, I just forgot the whole pseudo force thing going on. Oof. Find the velocity v dash of the sleeve related to the rod at the moment it reaches its other end B. I think I did this question once, like I completely did it, but then now I just don't have that memory. I don't want to do the pseudo forces stuff anymore. Just use angular momentum, right? Just use angular momentum, and then that's gonna do the thing. Oh god, this is not good. Um, I omega is equal to that. Sure, but then that just deals with the tangential velocity. What about the radial velocity? Doesn't that? What about that? Uh, Energy conservation. Sure, you could do that. There's the oh no, you can't. There's the normal force. Normal force is pushing it. So no, no energy conservation. Friction force is not. I get it, but there is the normal force. So you have to take that into account. And I don't know. I don't know how to this thing. You can't do angular momentum conservation unfortunately because this is moving with omega. It's powered by something that doesn't care what is going on. Okay, right. So you have to go for the pseudo forces. There's a centrifugal force. There is so like centrifugal force is just given by this thing. Wow, I really don't remember what was going on anymore. Oh god. Okay, what about this? So you got the acceleration, the net acceleration, right? You can just use that to do some stuff. So like because there's no friction, maybe you could use this thing to get something done, right? And then it's like moving it. Oh my god, I'm gonna do it. We'll see what happens. So just equal to what? Omega square r. It's like negative of that actually. So negative omega square r plus r alpha. All of that times the r hat vector plus so 2 omega r dot plus r double dot. Something's not right. Oh, r alpha should be over here, not over here. Okay, this is r double dot over here, and then it's got r alpha, and this is in the t hat direction. So if I don't do this according, you know what? No, it's so simple. You can do it. Yeah, you can definitely do it. This is the acceleration as seen in the total, the ground frame, not the rotating reference frame, but in the rotating reference frame, what's happening, right? Uh, it's like pseudo acceleration and whatnot. Maybe just do it in the ground frame and then you will go to the yeah. Okay, so in the ground frame, this is the thing. There is no friction, so there is really no force in the radial direction. Tangential direction, we don't care about that. And also like alpha is a zero because right. So this is yeah, you got some coil's force and something you don't care about that. You got this thing. R double dot is equal to omega square r. That's all you need to know because oh yeah, so like okay, that what that means is right. Okay. There's only the centrifugal force in the radial direction that you actually have to worry about. This is interesting, but I think I did have some other force in the radial direction as well. So what about that? Or was it completely in tangential direction? Huh. Interesting. I will have to see that once again. Whatever. This is the thing. So just solve this differential equation and you're good to go. Like, okay, you could write this thing as t upon t r of r dot square. Sorry, r dot square. Yeah, that thing in half is equal to omega square r. So r dot squared. Oh, and omega is like actually fixed quantity. Okay, r dot squared is equal to omega squared and then r squared. And yeah, it changes. So initially it was zero. It was zero because it was just accelerating right now. So yeah, and now at some value of r, just have r squared. So that does it. So you got this thing. You can write this as r dot is equal to omega r because it's never pointing inside. Okay, so it's going out. So that helps. We got this as our radial velocity. So like just got natural log of r going from something to something. And it's like omega naught actually. Yeah. So something. Oh, okay. This is weird. Because initially it's like it's zero. So then how does this even make sense? Initially r dot should be zero, so then it should take like forever to come out. It doesn't. Does that make sense? Yeah, okay. What would happen if this was what would happen? Sorry. Uh seasons changing. That's fine. So what would happen if your sleeve was really a point mass? Then it would just stay there forever, right? Because there is really no centrifugal force on this, so it would just stay there forever, which would mean it would not. Okay, that's what this is. Right, right. So if it is actually not zero, it's at some distance already, right? What do you actually want, by the way? Find the velocity of the sleep. Oh, you don't want the time required and anything, so just do the thing. Okay. So you got r dot is equal to omega r. So at r equal to what? At r equal to L, you just have like the rate of velocity is just equal to omega naught L. And also our tangential velocity, that is just equal to omega naught L as well. That rhymed. Okay. What does that mean? Just square root of 2 times omega naught L. There we go. That's our answer. Yeah. Do we care about this mass m, so the mass of the rod? No, we don't. Huh. Wait, okay, maybe this question can be interpreted in two different ways. One, it that there's an external force that is keeping it omega naught throughout. Oh, it might actually be just right. Okay, this could be problematic because either it's just omega naught constant, or omega naught is really just the initial angular velocity, and then it's actually changing, and there is no. Oh, this could really be problematic, right? Yeah, this could be really problematic actually. Oh no, because that would mean omega square is actually changing. Okay, this is the thing, and then oh yeah, this this equation, oof, omega squared r, right? And then you can't do that because omega is a function of r now, which you'll have to get through angular momentum conservation and whatnot. Oh, you can interpret it in two different ways. Just can't do it like the way I did, but then there's other path as well. Well, we'll see what's the thing. Next question, 273. I should really revise a bit because I did everything and now I don't remember anything. Okay, 273. Uniform rod of mass m and length L rest. So mass is 5, length is zero point 0.9. Rests on a smooth horizontal surface, or one of the ends of the rod is struck with impulse in a horizontal direction perpendicular to the rod. Just a horizontal surface, fine. One of the ends of the rod is struck with an impulse in the horizontal direction perpendicular to the rod. As a result, the rod obtains a momentum. Find the, so basically that's giving us what J is, right? Because, oh, okay, that is given already. Find the force with which one half of the rod will act on the other in the process of motion. Okay, okay. So with respect to like, okay, the center of mass frame is just inertia. That's all we need to know. So the acceleration in the center of mass frame is the same as the in the ground frame. So just do F equal to ma and yeah, get over it. So just figure out what omega is and then you're good to go. So it's like what? A uniform rod. So ml squared upon 3 is our inertia, our torque. Oh, actually, you know what? About the center of mass, it's a different thing. So it's like ml upon 2. So it's like ml squared upon 12 is our inertia. Okay. Now, um, this might actually not be the thing that I want to do. Whatever. And then you got torque, which is our impulse times this thing, L upon 2. You know what? Nah, I'm just gonna use R. So R is just L upon 2. So it's JR upon MR squared upon 2. That's better. So you got 3J upon MR. That is our omega. Okay. This guy's center of mass is over here. So this is just R upon 2. And then you got the force on this is like M omega square R. Right. M upon 2 because half of the mass. R upon 2 as well because R upon 2. Yeah. So that is the force. Alpha is 0 for this thing. So perfect. It's like just this guy, half M omega square R. That's pretty much the force put by these two halves on each other, right? Just figure that out. Oh, it's like 1/4, sorry. So 1/4 m omega square is just this guy square is like 9j squared upon m squared r squared, and then this times r. This cancels. One of this cancels. Is just 9j squared upon 4mr. Cool. Dimensionally, is this correct? So j is like kg meter per. Oh wait, no. Oh yeah, kg meter per second. So you might have like mv squared. So this is m squared v squared. So mv, okay, m squared v squared. So mv squared, and nothing upon r. So is that what is it? Once again, the force. It is mv squared is like energy that's 4 times the mass, 4 times the length. So this is also length. That works out. Calculate this thing. So 9. You know what? Just put this as the answer. You got what? 9j squared upon 4mr. And what is this equal to? So 9 times j squared. What is j once again? 3. Okay. Yes. So 9 times 9 upon 4 times of mass is just 5 times r is what? Length is this thing. It's like r upon 2. So you just write this 2 times of m times of. Yeah, you just write it like that. That's better. 2ml. Okay. And the length is 0.9. Perfect. This is 10. So 9 cancels 9 is the value. Next question. 274. A thin uniform square plate with side L and mass M can rotate freely about a stationary vertical axis coinciding with one of its sides. A small ball of mass M flying. Okay, so this is the thing. Square plate, side L, mass M, rotating freely about stationary vertical axis coinciding with one of its sides. A small ball of mass M. Yeah, I've done this question. Elastically, as expected, of course. Center of it, cool. Find the velocity of ball we ride in the horizontal component of resultant force which acts. Cool, no big deal. I can do it. So, uh, right. So for inelastic collisions, this would be like your angular rate of conservation. So you just have, or actually also that thing, well, whatever. So angular rate of conservation would just give us the final inertia, which is like I plus mx. So what was the thing that I did in that video where I actually derived this thing? So you got this as our axis, this is the rod, this is our whatever this was, right? In this case, just more generalized. And then you got m, it's yeah, it's hitting it at x perpendicularly, so this is x. Okay, so just have m I plus mx squared. You know what? You should just call this as a small r because whatever. So I plus mr squared times final omega would just be equal to, right? That's the final angular momentum. Is just equal to the initial angular momentum, which is like it's moving with what? Let's just say it's moving with v naught, so it's m v naught r, right? Yeah. And finally, your velocity is given by, so the velocity of this ball is just given by omega times r. So it's just going to be this guy, m v naught r squared, I think, upon I plus mr squared, right? Or you could just say it's like v naught times mr squared upon I plus mr squared. Now, that's good and all, but in case of elastic collision, what we actually have is v is equal to v naught times mr squared minus I upon mr squared plus I. Yeah, that's the thing. That's the thing. All right. So that's gonna do the A part, so velocity of ball after the impact, and also the horizontal component of the result. That is easy to figure out once you figure out what V is. So, oh wait, what? Resultant force which the axis will exert on the plate after the impact. Oh, so, oh, you mean like that, huh? It's elastic, it doesn't stick to it. That's important. Yeah, okay, that's equal to no big deal. It can be done. For that, you just need to know what omega is. And then this is the omega for inelastic collision, but then for elastic collision, just got 2 over here. So that works. This is the thing. Oops. Just calculate these values first of all. And you know what? Actually, no. First, we'll just calculate what the force is. So force is just equal to the mass of this plate, and then you got, what is this? M omega square R, right? And then alpha is zero, so we don't care about that. Yeah, the centripetal force. That's all we care about. So you got omega squared, and then R, which is just L upon two. That's the thing. So yeah, just figure out what omega is, and then you're good to go. Basically, like M omega squared times R, wouldn't you say? Because this is just equal to R, right? You know what? Just do it like that. And also I is equal to ml squared upon 3, but that's like m times 2l squared upon, so 2r squared upon 3, so like just 4 upon 3 mr squared. Does that make sense? And just put that over there. So v is equal to v naught times m minus 4m upon 3 upon m plus 4m upon 3. What are the values? Oh, so they didn't give us any values, huh? Whatever. At least that we know now. So just our v dash, right? And this was actually our v. Doesn't matter. This is all we need. So yeah, well, that's done. And also this force. So what's our omega? First of all, omega is just 2 mv naught r upon r plus m r squared, which is just you know 4/3 capital M plus small m times r squared. Like it just cancels. You get this thing. Perfect. So 1 square of this guy, right? So omega squared is equal to 4m squared. Yeah, it's gonna get complicated, but whatever. It's like 4, and then you could do that to really do that. Whatever. 3m upon 4m plus m squared. You got v naught squared upon r squared, right? Let's put that in this guy. So m omega square r, m omega square, it's r. So 4, and then you got all of this 3m upon. Oh, this is supposed to be 3m, sorry. Okay, then it's just taking forever. See, that's why I did this derivation already. So got v naught squared upon r squared, and then if they have given us the values, it would be much easier to write down. What was it once again? This time's r, right? So v naught squared upon r. This is the thing. Okay, you got the thing. So b, you got the value. You could write it differently, but whatever. So you got 4m. You know what? No, just write it the best way. So this is the thing. Okay. And by the way, r is just for L upon 2. So 72 over there. That's the thing. So that's our B answer. What about our A answer? So it's this guy. Right. 3m minus 4m. Next question. $275. A vertically oriented uniform rod of mass m and length L can rotate about its upper end. A horizontally flying bullet of mass m strikes the lower end of the rod and gets stuck in it. Rotate about its upper end. Okay, vertically oriented uniform rod. Fine. As a result, the rod swings through an angle alpha, assuming that m is less than capital M, so much less than that. Fine. The velocity of the flying bullet. Uh, oh, okay. So the maximum alpha. Okay, that's alpha. The momentum increment. Okay, whatever. First of all, just deal with the system. You want the velocity of the flying bullet and momentum increment in the system bullet rod during the impact. What causes the change of that momentum? Momentum increment. Wait, what? And flying fine bullet of mass strikes into the end of the rod and it gets stuck in it as the rod swings during alpha. What do you mean by increment? It's like a decrement, I would say, right? During the impact. Of course, the hinge force is what's causing the change. So what do you mean by the momentum increment? Oh, okay, just during the okay, fine, no big deal. So during the impact, okay, what causes the change of the momentum? Huh? It just sticks to it, right? There's the hinge force, sure. Is it along the horizontal direction? I think yeah, there is a horizontal hinge force. Otherwise, what's gonna cause it? The gravity is completely like vertical and everything. Okay, whatever. Um, right. At what distance x from the upper end of the okay, fine. Momentum of the bullet system, the bullet rod system to remain constant. Cool. Let's do it. Fine. Let's do the thing. So you got this guy, mass m, length l. This is our rotating axis. You got this guy with x. It's hitting non-elastically, right? Okay, so we can figure out what omega is after this thing. So omega is just going to be equal to okay, what was the thing once again? I just forgot about it. What was the thing? Oh yeah, like angular momentum, right? So you got, maybe I should just call this small r, but whatever. Yeah, just call it x. So m v naught x. Just the same thing as the last time. What's the difference? Just is non-elastic. That's all the difference. Okay, it's gonna take forever actually. Here's a better way. Here's a better way. So you got angular momentum squared upon 2 times inertia. That's also a way of giving out the kinetic energy, right? Angular momentum we already know. Even after collision, angular momentum is still the same. So that doesn't really change anything. Inertia, right? So after collision, you can figure that out, and then you got the kinetic energy. So that's awesome. This is just angular momentum, in fact. And you know what? Actually, yeah, call this thing R because it is better to use it like that. So this is like m squared v naught squared r squared upon to inertia. So inertia, the whole thing, it's like mr squared plus ml squared upon 3. Cool. That's the final kinetic energy. And what's the potential energy at any given moment? Wow, that's weird. Oh yeah, okay, this is the kinetic energy just after impact. Because after that, element is gonna change because gravity, right? So yeah, that gives you our angular momentum. Cool. Sorry, our kinetic energy. And what's our potential energy? Okay, the change in kinetic energy is like what? This is also equal to delta K in fact. And the change in potential energy is just equal to what? It increased, but by how much? If this angle is alpha, then this guy like, okay, it went up by m l upon 2 times 1 minus cosine alpha, right? And then you have got g as well actually. So mg l upon 2 by 1 minus cosine alpha. And this other guy, right? It's like small m r, small m g r, 1 minus cosine alpha. That makes sense. Okay. So this will just be equal to g times of this thing. So we wanna what we want to figure out velocity of a flying bullet. So like this actually happens. I mean, just equate these and you get the thing. That's horrible. It's just so much all over the space, all over the place. First thing first, write it like that. It's gonna be g, right? You got sine squared alpha. Yes, bro. Hey, first of all, do you even want this? No, you want this for particular r value. Oh, b is what you want for like variable r. Momentum increment in the system. Okay, that's just for this thing as well. C is what you want. So you want the momentum increment, right? Okay, cool. So you got angular momentum. From there you can figure out the angular velocity, and then yeah, finally just get the total momentum, the linear momentum actually, right? Okay, so you got delta U and delta K. We don't care about that really. Okay, so what's your omega finally? It's just L, which is mv naught r upon, okay, mv naught r upon the now inertia, so like mr squared plus ml squared upon 3. Okay, once you have omega, figure out the momentum, which is, so you got what, ml upon 2 omega. That's right. Okay, and you got mr omega, which is, once again, just ml upon 2 plus r, sorry, mr times this thing, right? This is the final momentum, and then minus the initial momentum is the change in momentum. So initially it was what? Initially your momentum was just mv naught. So once we are done with this, we'll get the value mv naught, and then you got all of this. Oh, it's just taking forever, isn't it? What we could do is just say, okay, r is equal to k times l. That's gonna simplify some stuff. So, right. I mean, hopefully this simplifies some stuff. So like m, you got 1 upon 2, so m upon 2 plus m times k, and then take out that l, and then you got this. That is gone. Just got v naught r forever. Oh god, how long? How long do we have to wait for this? This was a bad idea. Mk squared plus minus 1. Probably also this thing, we'll just say m is equal to eta l, so eta m, just like all the time. So you got what, mv naught eta upon 2 plus, and then you got like that m cancels out and whatever. So m upon 2 plus, so eta upon 2, then you got plus k times l. Oh, by the way, this is gonna have l squared, so like you can just do that thing. And also you got r over here, so that's just k times of l. Cool. Some stuff cancels out at least. So this is there. Is this correct or not? Looks correct. This extra V not over there. Why is that? What's that doing over there? Wait, is that supposed to be the? No, no, it's not. It's not this thing. It's just MV not R. Sorry, angular momentum, right? So it's not supposed to be here. Perfect. And then you got this. So that L is not here anymore. K upon K squared plus eta upon 3. Okay, minus 1. Ah, it's just taking forever. So what can we not? Do you really want to do this thing? Not me, at least. I don't want to do it. But you have to get it done. 6k squared plus 3k eta minus 2 eta. Then you got what? Minus 6k squared once again. This cancels at least. So just this guy, eta times 3k minus 2. All that upon this thing, 2 times of eta plus 3k squared. That's the thing. This thing times mv naught. Right. So finally we have an expression for this. Okay. Cancel everything else. And most likely it's going to be wrong, because when you have a lot of calculation, you get wrong solutions. We don't want all of this, just want this thing. That's the change in momentum. So at what value x, so what value of r basically, this change will be just 0, Okay, so B and C, we answered that. It's this thing. What C? C, for what will be, it's going to be 0. There's only one way that happens when k is equal to 2 upon 3. So yeah, r is equal to 2 upon 3l, right? So just 2 upon 3l. That is the thing. Okay, perfect. And let's do A now. So for A, what's happening? So a horizontally flying bullet of mass m strikes the lower end. So our r is just equal to L, in fact, right? Okay, so now we can do this thing. So just rewrite everything. K is equal to stuff. R is just equal to L. So you got m squared v naught squared upon, it's like 3 out. Then you got 2 times of m. It's like 3m actually. It's capital M, right? I think. Okay, and that's gonna be equal. Okay, and what's our u, by the way? Delta u actually. So one of this stuff is just equal to that. So g l uh, g l m plus 2m. That's the thing. Okay, just equate these and get your v naught. It'll take forever, right? So what do we have? Oh, that's gonna go over there. This is just really bad. So v naught square is just equal to 2gl and then multiplies out. Seriously. M squared plus 5mm plus 6m squared, and all of that upon 3m squared, and that times of sine square of alpha upon 2. Okay, at least we got an expression. So what do we have? Just have, or you could use this thing, right, to do it better. So this in more compact form can be done as 2gl upon 3, and then you got all of this. 1 plus 5, oh sorry, should be like this thing. Eta plus 5 eta, or you know what, no, just write it like eta plus 2 and eta plus 3, but that's better. You got sine square alpha upon 2. So this is equal to v naught square, so like v naught will just be equal to square upon that stuff. So square root of 2gl upon 3 square root of eta plus 2 times eta plus 3, and then finally just got this thing, sine of alpha upon 2. So you got this expression. This thing is your A. Yeah, okay. You know what? These are like more fundamentally smooth. I mean, here. And these are our final results. Oh, and by the way, for this particular case, we already know what eta is and what k is, right? Because, yeah, k is just 1 and eta, okay, we actually don't know what eta is. Huh? But at least we know what k is. So k is just 1. This is going to be eta, just eta, and then upon 2 times of 3 plus eta, right? Okay. This is going to be equal to what? Mv naught eta upon 2 times of 3 plus eta. Perfect. Next question. Yeah, that should do it. No big deal, right? Uh, yeah. And we know where it comes from, what this momentum comes from. It's just the hinge force. 276. A horizontally oriented uniform disk of mass m radius r rotates freely about a stationary vertical axis passing through its center. The disk has a radial guide along which can slide without friction a small body. Wow, so poetic. How did you not tell me this directly, but in a loop fashion? Okay, a small body of mass m. A light thread running down through the hollow axle of the disk is tied to the body. Wow. Okay. I, yeah, I think I'm getting what's going on. Okay. Thread running down through the Initially, the body was rotated at the edge of the disk, and the whole system rotated with an angular velocity omega naught. Then, by means of a force F applied to the lower end of the thread, the body was slowly pulled to the rotation axis. Find the angular velocity of the system in its final state. The work performed by the force F to the rotation axis. Okay. Huh. Interesting. So, okay, you just have to do angular momentum conservation because the force F doesn't actually have any torque associated with it, right? So the whole system still has the same angular momentum, right? Okay, that makes sense. So the angular velocity system in its final state, you can do that easily. And the work done is just the change in kinetic energy because there's no other force that does any work, is there? I don't think there is. The hinge forces don't do anything, no work. And what other forces do you have? Nothing, right? So that's the thing. Yeah, that's the thing. Okay, the angular velocity system in its final state. First of all, figure that out. So what is the angular momentum? Initially the bodies were at the edge of the disk. Inertia initially was just mr squared plus mr squared upon 2. In terms of omega naught is equal to, finally this guy doesn't have any inertia, just mr squared upon 2 times omega. So that's what actually easy. All right, it's just this thing. Oh, and it's just capital R squared as well. So yeah, yep, that should do it. That's the first answer. This is what A, and this is actually a question that I got much before solving this thing, right? Because I even made a video on this when I first got a question like this. So I don't know if it was exactly this question, but I got in one of these space modules and I made a video on this. What was this like? The rotational, no, what? The energy of rotational bodies, right? Rotating bodies. That was the video. Whatever. Go watch it if you want to. B. The work performed by the force F, right? So it's just like what? The force F times the change in the, wait, F is like a variable force, right? Of course. So you do want like, oh, in that case, you can't just do F times that. Right, so you have to go for the delta K thing. No big deal. So our angular momentum is still the same. It's just equal to this guy, like, and then you just want L squared upon I upon 2I. That's our inertia and whatnot. Yeah. Should we? Think about it. It's like what? L squared upon 2 times 1 upon I final minus 1 upon I initial. This is the change in kinetic, which is like the work done by this thing, right? Interesting. So that is L squared upon 2 times of I initial minus I final upon I final, that's I initial. Alright. This we know what to do, no big deal. Now L is just equal to I initial times omega naught squared. So just do that over things like what? I initial upon I final omega naught squared. You got this 1 upon 2 over there. Well, yeah. What else? And then you just got this thing I initial minus I final. Yeah, that should do it. So let's do the thing. Half I initial upon I finally already got the expression, which is actually just this thing. So yeah, upon m times omega naught squared, and then you got this thing. So initially you had what mr squared plus all that stuff, and then finally just got this. Okay, it's gonna be what mr squared. That is the change. Capital R squared. Yep, that should do it. So what is this going to be? This is like 2m plus capital M times small m upon 2 capital M times omega naught squared r squared. This is the work done. Next question. 277. A man of mass m1 stands on the edge of a horizontal uniform disk of mass m2 and radius r, which is capable of rotating freely about a stationary vertical axis, passing through its center edge. Okay. At certain moment, the man starts moving along the edge of the disk. Okay, she shifts over an angle. What is this thing? Phi dash related to the disk and then stops. In the process of motion, the velocity of man varies with time. Oh god, okay. Oh, I thought it would give an explanation. No, it doesn't give that. Fine. Assuming the dimensions of the. This is weird. Related to the disk and it stops. Something's weird about this thing. Man starts moving along the edges of the disk. Right. Okay. It's not moving radially. It's moving along the edge. He shifts over an angle phi due to the disk and then stops. What? Why? So it's like, okay, in the process of, oh, okay, that is like final initial state. That's all they're saying. I thought it's going like, it's starting then stopping, starting and stopping. That would make a perfectly hard question, right? I thought they would do something like that. Right. In the process of motion, velocity of a man varies as v. Assuming the, why is this v dash? So this is with respect to what? I don't know. Fine. Assuming the dimensions of the man to be negligible, find the angle through which the disk have turned by the moment the man stopped. Hmm. So yeah, I get you want to do angular momentum preservation, but no, here it is a bit. All they've given us is what angle phi dash is. Okay. The force related to the rotation axis which the man, huh. Okay, the force related to the rotation axis which with which the man acted on the disk in the process of motion. Wait, what? The force moment? You mean the torque? So the instantaneous torque or what? You want like the angular momentum change or something like that? Because how am I going to do this v dash if I don't know how it depends on time? Anything about uniform motion, something he shifts over an angle of phi to the axis and stops the process of motion. Well, no, nothing's given about uniformity. So how am I supposed to do this thing? The b part would be so not doable because I don't know how v changes with time. So then how do I do this thing? Right? Or do they just want like the total? Yeah, I think by the moment they just like they want the angular momentum that changed or something like that, right? I guess. Yeah. Okay, fine. Let's just do the thing. So with respect to the disk, the man is like going with some kind of angular velocity omega. Okay. And the disk is moving with angular velocity omega naught. And both of these are like variables. So omega naught we are generally used for constants, but those are variables as well. Or you know what? Okay, if you really want, Just use omega dash and omega. Right. So the actual angular velocity as it's in the ground plane is like omega dash plus omega for this guy, right? But of course, omega dash is what we call as like d phi upon dt. So yeah, phi dash is just integration of omega dash dt, right? Okay, now we just need an expression between omega dash and omega, and yeah, we will be good to go. So in that, we just integrate that and get the thing done. Cool. So right, um, that's like omega dash. Let's look at that guy and think about it. The torque because of that is the same torque because of that thing, right? That's one thing that you can do. So with respect to this guy's like moving with omega dash, but then actually it's moving with omega dash plus omega, right? So the inertia of mass, like it is called capital M times R. You know what? No, it's called small m. Small m r squared times omega plus omega dash. That is equal to, and omega is just the velocity of the disk. So this point with respect to ground frame. That makes sense. Okay, this is equal to. Oh, sorry, it should not be this thing. It should be this. I think negative. Yeah. Well, no, I think this is like moving it faster, so it's gonna be omega dash minus omega because this guy's inertia should be like less, and then this guy's inertia just so it's a uniform disk. Yeah, well, it's mr squared upon 2. That is omega. That's the thing. Okay, so um, what do you have? Omega dash minus omega is just equal to 2 m upon 2m times omega. So omega times, and then you just integrate this thing. So the angle by which the disk turn called theta. I don't know. So yeah, that is just going to be equal to phi dash, right? Right, exactly. So there we go. That's the thing. And we also want the force moment related to the rotation axis with which the man acted on the disk in the process of motion. That's a hard thing actually because it changes, right? So yeah, but what we know is that finally this both of these actually they just have angular momentum being equal to zero because it just stops, right? Yeah. So man stopped with respect to the disk. Basically, like angular momentum should go to zero because it started with zero, right? Conserved, right? That makes sense. So the total angular momentum change of the disk and man, both not combined separately, is zero. So B should be zero, I think, right? Because this doesn't make sense. At some particular instant, how do I figure out the torque? I don't know how to do that, given this, right? Or maybe we can. Oh, what I think is maybe they are giving us like find that with in terms of V dash, right? Because even though they didn't actually give us what V dash is, they could have, right? So for a generalization, just find it out using V dash. Does that make sense? I guess it does. So you already got what omega is in terms of omega dash, right? And the velocity of man, wait, within what frame exactly? Ah, they didn't give us what that is. But okay, phi dash is related to disk, so I'm assuming this is also related to the disk. So v dash will just be like omega dash times r, right? In the tangential direction or whatever. Okay, that's how the velocity changes. Cool. Right. So just need to figure out this thing in terms of omega dash. What do you want is the torque. So you differentiate this thing, you just get like alpha times that. So like alpha is equal to 2m upon m plus 2m times our d omega dash upon dt thing. And then you want inertia of that. Oh, that's just not. Oh, that's like weird. Oh, okay, that's gonna be the same as that. Fine, dl upon dt is the same for both of these guys, magnitude wise. So for this guy, what is our dl upon dt thing? It's just gonna be this guy. So yeah, You could do this, right? Well, whatever. And what's the inertia of the disk? It's like m upon 2 r squared. So just put that over there. So torque really is this thing, m squared r squared upon m plus 2m. And then you got this. So what's alpha dash, right? There we go. That's the answer for this guy. So there we go. That's our answer. A, you got this theta, which is just 2m phi dash upon capital M plus 2m. And B, you got this as the value. So m squared r squared alpha dash upon m plus 2m. Right, that's our torque. So torque at any given instant. Does this make sense dimensionally? Alpha r is acceleration, so you got acceleration times. So first you just got the mass, m upon all that stuff cancels. We don't want units of that. So just m times alpha r is force, that times r is torque. Makes sense. So that's it, 277. Okay, 278. How much is remaining? Oh, quite a lot actually. Yeah. Ooh. So 289. We'll have to go till that. Fine, we should stop right now. See you guys in the next video.